Dear students, today we are dealing with one of the type of mechanical energy, that is potential energy. What is potential energy? The energy possessed by a body due to its position. It is always associated with restoring forces like spring force or gravitational force. For example, the work done in stretching a spring or lifting an object against a force is stored as potential energy in the spring or in the object. In general, potential energy is the energy difference between the energy of an object in a given position and at the reference position. We should know that always potential energy is treated as a difference in energy. One kind of potential energy is gravitational potential energy. As we all know, we calculate it as mg delta x, which is nothing but force into distance. Mg is the weight gravitational force and delta x is the distance the object has been lifted through. M stands for the mass of the object, g stands for acceleration due to gravity, and delta x stands for height above the ground. The other kind of potential energy is elastic potential energy, which is given by half kx square. We know that F is equal to minus kx, which we will be dealing with the same equation. We will be dealing with this equation. K is the spring constant and x stands for extension or compression of the spring. Now, how we have derived this half kx square will be dealt. So, let us move on to the spring and Hooke's law from potential energy. As we all know that experimentally it is proved that extension of a spring is proportional to the force applied to it. This is known as Hooke's law. Now, I can write it as F is equal to plus kx if the force considered is the applied force. As you see here, the spring without any force applied, it is in its equilibrium position, there is no extension. When a force of F Newton is applied, the extension is x. When a force of 2F Newton is applied, the extension is 2x. Here, F stands for the applied force, x stands for the displacement of the spring's end from the equilibrium position, and k stands for the spring constant. Now, the actual law mathematically is written as F equals minus kx. Here I have specified F as Fs to show that Fs stands for the restoring force exerted by the spring, which is also called as spring force. You should know that when a force is applied along the spring externally, within the spring, the molecules exert a restoring force which always tries to bring the object or the spring back to its normal position. There is a limit for the force that can be applied. So within the limit, if the force is applied, always the spring force, which is the restoring force here, brings back the spring to the original position. So you should know that the applied force and the displacement are in the same direction, but the spring force and the displacement are in the opposite direction. Hence, we apply a negative sign in this situation. So, Hooke's law is Fs equals minus kx, but the negative sign shows that spring force and displacement are in the opposite direction. Let us look at how this is represented graphically. We have here the graph, which is, you can observe this graph here. So, in this graph, force is along the y-axis and compression or elongation along the x-axis. Now this is a force displacement graph, and slope of the graph gives the spring constant because it is F by x is K. Now we can see that the elongation is in the positive quadrant, whereas the compression is in this negative quadrant. Now the dotted line shows the actual variation when you stretch a spring. The bold line shows the ideal situation where force and displacement are directly proportional. Now, how do you calculate the potential energy of the spring graphically, which is called elastic potential energy? If you have applied force on the y-axis and displacement along the x-axis, look at the situation. The force applied varies from 0 to F. So the variation may not be uniform. So we have the average force will be F by 2. So we can find the area under the graph, which is force into displacement, which gives the work done. So the area under the graph is half BH, which is half x into F. Since F is Kx, we can look at the situation again. Here, look at the graph. You can see that half into BH is half xF. F is equal to Kx. So if you substitute in place of F as Kx, you get it as half Kx square. That is one method. Or you can also say that the work done is average force into distance, which means average force into x is half kx into x, which is half kx square. So in general, you can see that the elastic potential energy is given as half kx square. And so the two types of potential energy, gravitational potential energy and elastic potential energy, are given by mg delta x and half kx square. Thank you.